let's see. Okay, so, excuse me, in section 3.1, we're going to be looking at polynomials of higher order than just quadratics and understanding some things about their graphs based on the roots and everything like that. So I am attempting to record this. Hopefully it'll work. And then, so I need to also hook up through this system to be able to have the recording show up. So let's see if I can get this working. Okay. Okay, so just as a bit of a review, a polynomial is a function of the form what we have some highest power that we're raising it to. We're going to have coefficients, so we could say c sub n x to the n. So you just have powers on x added together. The coefficients just have to be real numbers, but those powers on x have to be whole numbers, right? Or natural numbers. Okay, so these are what we're going to be looking at. We've spent a lot of time on quadratic functions, right? The ones where you only go up to a second power on x. We had that one example in the previous section where we had x to the sixth or something like that, right? But it was a special case where we were able to reduce it to a quadratic to look at it. So we're going to start looking at what can we say about a polynomial, right, when the highest power is higher than 2. Okay, so a couple things that are true about every polynomial. They're always continuous on all of the real numbers. And they're also smooth. I'll put that in quotes because we haven't really defined what that means. But essentially what it means is there are no sharp corners like there is in, for example, an absolute value function has that sharp corner at the vertex. Like there's nothing like that. right? No sharp corners. And when you get to calculus, you can define that in a more rigorous way. Okay, so we're going to have a little bit of terminology. Let's say let A be a zero of a polynomial. Okay, that means f of a equals 0, right? If you plug that in, you get 0, or it's a place where that function crosses the x-axis or hits the x-axis. We're going to say that a has multiplicity k if x minus a shows up k times in the factorization. Okay, so let's say, what is the multiplicity of 1 in the polynomial, let's say just x squared minus 2x plus 1 equals 0. Or actually, I'll just write it as f of x equals this. And so to figure that out, we would need to, factor this polynomial and then see how many times that x minus 1 shows up in it. So if we factor this, we're going to get x minus 1 times x minus 1, right? Or x minus 1 squared. So since it shows up twice, we're going to say that this root has multiplicity too.
That being negative doesn't, or positive doesn't make a difference.
Well, so the root is positive 1, and then the corresponding factor is going to be x minus 1, right? So yeah, we're looking for x minus that root, how many times that factor shows up. Now, we need to understand what happens based on whether a root has multiplicity that is even or odd. So in this case, if I were to graph this, I could take just the standard parabola of y equals x squared and shift it how? Yeah, to the right by 1. And so it's going to look like something like this, right? It's going to hit the axis, but it's only going to touch the axis and then go back up. It's not going to cross through it, right? And this is what we can expect to see happening when you have a root of multiplicity 2 showing up. Okay. So in your homework, let's see, I think I got that open on here. trying to do everything on the iPad because that's where it's recording today. So, question 2, I think, is just this conceptual question where it asks, if r is a real 0 or a root of even multiplicity of a function, then the graph of f blank, the axis at x equals r, and our choices are just touches and crosses. Well, in our little example there, what happened? We had even multiplicity because the multiplicity was 2, and then what happened at x equals 1? Yeah, it touches the graph. And it turns out anytime it's an even multiplicity, that's what's going to happen. Okay, so that tells us a little bit about how a graph is going to look. If we can find the roots, then we'll be able to use that. And then the next thing that we're going to look at is what's called the end behavior. Oops. So what's going to happen is as your values of x get really large, either really large positive values or really large negative values, then your polynomial is going to start to behave like essentially a simplified version of that polynomial, right? And so if I have, let's say, for example, I have a polynomial that looks like this, then as x gets really large, then this term, the x cubed term, is going to be growing faster than any of the others, right? Everything below that will grow at a slower rate, and eventually what's going to happen is this x cubed term dominates everything else, right? So if we start looking at, okay, so I better get Desmos on here. So if we take this, okay, what was it? It was x cubed minus 2x squared plus 4x plus 4. Okay, this is going to take me forever to type stuff on this. Wrong button. Okay, what did I say? Minus 2x squared. Plus 4, is that right? Okay. So we have something that looks like this. So what's happening kind of around 0 in this small area is affected a lot by these other terms. But as you get really large in your x values to the left or to the right, if you just compare this to x cubed, what's going to happen is those are going to start to behave, a lot like each other as you go on, right? That's the idea, is that it's really that x cubed term that's dominating, and if you go farther and farther out, they start to move right along each other. Okay. All right, so it's really that just highest order term that's going to be the most important in the growth as x gets large. Okay, so when we have an example like this, the graph of the function is going to behave like what for large values of x? Yeah, it'll behave like this term, 2x to the fourth, right? So we want to look for that highest power term right there, right? And it's going to start looking like that over time. So nothing too complicated about that, right? Okay, so let me even throw, maybe just to make sure that we see what happens if you have a coefficient. When they say as absolute value of x gets large, they're just saying as x gets really far from the origin to the left or to the right. So it'll behave like the highest order term, 2x cubed. So that gives you an idea of what the graph looks like as well. So what we're trying to do here in this section is understand how a graph looks without necessarily knowing all the details about the graph, right? So we've got the end behavior. Another thing that's going to be important would be turning points. Okay, so turning points on the graph are going to be where we switch from going up to going down, or switch from going down to going up, right? And so for a quadratic, how many turning points are we going to have? Yeah, for a quadratic, you're always going to have one, right? So here's a turning point. But as the powers get higher, it gets a little more complicated, right? If we have a cubic function, right, we have a couple of possibilities. If you just took y equals x squared, or x cubed, I mean, it looks something like that, right? So how many turning points would that have? So where does it turn around from going up to down or down to up? Versus some other cubics are going to look like this, right? So here we turn around from going up to down, and then we turn around again from going down to up. So we would say that has two turning points. Now, whether we count this one is going to depend on how they define turning points specifically. All right, so let me see if I can find an example where they because I think that would be, if we're calling it a turning point, I would say that this has no turning points because it never switches from going up to down, right? But we'll have to see how they define it. So let's look at this one. The graph of, we have y equals 5x to the 6 minus 3x to the fourth plus 2x minus 9 has at most how many turning points? Now, we saw that a quadratic had at most, or had one turning point, right? A cubic has at most 2. Right, so if you have a third power polynomial, you can only have up to 2 turning points. If you have a sixth, what are you thinking we would have? Up to what? Yeah, it would be up to 5. All right. Oh, I didn't show it on my video. Which one was it? Yeah, so this graph has at most 5 turning points. All right. In the parts of this section where they're asking us to find the graph, we're going to have to use a few different details of what we know about graphing polynomials to pick the right one, right? So first off, with a polynomial, if it is even degree, then what do we know about the end behavior? As we go out far to the left or far to the right, are those two ends going to go the same direction, either both up, both down, or are they going to go different directions, one up and one down? If you have an even degree, it's always going to be the same direction. And if you have odd degree, then they'll always go opposite directions, right? And which directions they go on that odd degree is going to depend on the coefficient on your highest power term, right? So here, our highest power term is going to be an x to the fifth, and if you multiplied this out, right, it would be positive x to the fifth, right? And that means as you go to the right, you're going to come up from the direction of minus infinity, and then as you go to the right, you'll go up towards positive infinity. So it's going to be one that looks like that. In this case, it seems like they all do. So what else could we use?
It's going to be shifted 2 over to the right and 5 up.
Good. Yeah, so what the other thing that we're going to have to use is the shift. Right? We know x is replaced with x minus 2, so we can say that's a shift to the right by 2. We add 5 on the outside, that's a shift up by 5. So now you're looking for which of these shifts that center to the right 2 and up 5. A looks like it shifts maybe to the right 2, but down 5, right? So that's not the one. B looks like to the right 2, up 5. I think that's going to be the one. Right? The other two are definitely not shifting to the right, and so it's got to be that one. So we can use the end behavior, we can use shifts, and hopefully together those are going to give us enough information to figure out what's going on. This next one is essentially the same idea. We have 7 times x plus 1 to the fifth plus 3. So we know we're shifting to the left 1 up 3. We know that this is odd degree. So since we have a positive coefficient on x to the fifth, we know that as we go to the left, we're going to be going down towards minus infinity. As we go to the right, we're going to be going up towards positive infinity. So let's use all of that information. So we know the shift is to the left 1 and up 3. I am seeing, I can eliminate 2 of these from that, right? I can eliminate C, that doesn't have the correct shift. That center value is not up 3. I can eliminate D, because that's not left 1. So we're down to these two, A and B. Those, okay, so now B also doesn't have the correct shift, it looks like, right? Because I want to go to the left. Yeah, so this one, again, you can do totally based on the shift. Does that seem right? Okay. Let's see, I need to talk now about building a polynomial from zeros. Okay, so let's say we know the zeros of a polynomial and we want to build a polynomial that satisfies that has those zeros. What should we do? Yes?
Since x is equal to all those numbers, you can flip them over the side of the equation, so x is equal to those numbers, just negative.
Okay, so
Multiply those together.
so we know that a number r is a root of the polynomial if and only if x equals r gives you a zero of the polynomial, right? So we could say if and only if x minus r is a factor of f, right? This doesn't tell us whether x minus r is a repeated root, but maybe from other information we're given, we could do that. So, for example, number 7 is going to ask you to form a polynomial whose degrees, or whose zeros and degree are given. Okay, so this one gives us 3 different real zeros. You have -3, 3, 1. And it says it's degree 3. So how are we going to build a polynomial that has that?
X power 3 plus x power 2 plus x plus a.
Okay, yeah, so for each of these zeros, for each zero, I should have a factor that looks like x minus that zero, right? And so I'm going to take x minus -3. X minus 3 and x minus 1. So typically, I'd probably skip writing x minus -3. I just want to make it really clear. All 3 of these are coming from, we're writing the factors for each of those roots. So we'll have x plus 3, x minus 3, and x minus 1. Okay, now my math lab tells you to simplify your answer. I'm not sure I really like that terminology, but I think they mean multiply this out, right? Right, the general form. So let's see what we get if we do. I'm going to take these two, multiply them together first. So you'll have x plus 3 times x squared minus 3x minus 1x, so minus 4x plus 3. And then to multiply this out, I'm just taking every term from the first set of parentheses, multiply it by each term from the second, right? And so I'll take x, multiply it all the way through the second. And now I'll take 3 and multiply it all the way through the second. And now I combine, right? So I'm going to have x cubed. We have minus 4x squared plus 3x squared. So I'll get minus x squared plus 3x minus 12x, so minus 9x, and then plus 9. Let's double check, but I think that's what they want for a simplified answer. Yeah, that's what they wanted. My problem with that is, to me, simplified means it's giving you more information, and this gives you more information about the polynomial than this form. So, I don't know. But whatever, we'll follow what they said on that. When they say simplified, they mean multiply it out. Okay, so if I'm given another one, here's another situation, same idea. You have your zeros are at minus 6 with a multiplicity of 1. It gives you 4 with a multiplicity of 2. And then it says it's degree 3. So what is a polynomial that satisfies those going to look like? What should my factors be? Okay, good. That minus 6, when I take x minus negative 6, I'll get x plus 6. And then that multiplicity 2 is just telling us we're going to have the factor x minus 4 twice. And so that would be a degree 3 polynomial. And again, you want to just multiply that out. Any questions so far? We're doing okay? We're gonna step it up one notch from here. So the next one says find a polynomial we want the zeros to be minus 3, 2, and 5 that passes through the point 672. Okay, so let's assume that we're finding a third degree polynomial, right? And so if we did what we were doing before, we would just say, well, a polynomial that satisfies this would be x plus 3 times x minus 2 times x minus 5, right? And I could multiply that out. However, this polynomial is probably not going to go through this point. So, but the one thing that we can do to change this polynomial, right, would be to do a vertical stretch on it, and that's not going to change the factors, right? And so then we're going to have to use that vertical stretch to make it so this polynomial goes through that point. So what do we need to do here? How are we going to figure out what a needs to be?
We're gonna plug in the x and y.
Good. Yeah, you want to plug in your x and your y. So this is going to be x. This is going to be f of x or y. So we're going to say 72 should equal whatever a is times, and now I'm going to plug in 6 everywhere, right? So I'm going to have 6 plus 3, 6 minus 2, 6 minus 5. So 72 equals a times 9 times 4 times 1. Okay, so that's working out really nice. We have 2 is equal to a. So now what you could do, and it says simplify your answer again, so we could say f of x is going to be 2 times x plus 3 x minus 2, x minus 5. And now multiply that out to get your polynomial in simplified form. You following that process? So really the only freedom that we had there was to do a vertical stretch because we needed to keep all the same roots. And so we just threw in an a value there, plugged in our point to find out what a would have to be for it to go through that point. Okay, there's going to be a couple questions like that. There are a couple where you're going to be looking at the graph. Let's see, I gotta zoom out here. I think 11 was one of those. Yeah. So this one just says determine whether the graph could be the graph of a polynomial function, and if it could be, list the real zeros and state the least degree the polynomial can have. Okay, well, I think we've got to be able to look at this polynomial pretty closely. To do this, what are our zeros here? Good, -3, 3, and 4. And so if we have the zeros -3, 3, and 4, then what would our polynomial have to look like to have those 3 zeros? Well, so if we have 3 roots, we would need to have at least degree 3, where we take each of those roots. So we could do something like that, right? So where it says, it's going to ask us, does the graph show a possible polynomial? Yes, it could be a polynomial. The real zeros are, you put in your values, and then it says the lowest degree the polynomial could have to get all 3 of those zeros would be 3, right? Are we okay? Here's another one where we're given the graph and we're supposed to construct a polynomial for it. Right, so let's look at each of these. Let's look at each of the hints we have here based on the graph. We can find the zeros. Is it going to let me? Come on. I don't know why, but this one doesn't want to let me pop the graph open, but I can zoom in on it. So here's our graph. What are our zeros based on this?
-2, 2, and 4.
Okay, -2, 2, and 4. I know that much so far. What does the multiplicity of 2 here have to be? At least 2, right? It's got to be even. So if we're doing the smallest one we can, it has to be 2 to just touch the axis and not go through it, right? And so we're going to have 2 with a multiplicity of 2. So we have -2, 2, and 4. Okay, so this is 12. And I'll add the graphs in on both of these so that we can see them. But we had what? We needed -2, 2, and 4, and 2 had a multiplicity of 2. And so we know that our function has to look like, if we use the lowest possible degree, it's going to look like what? What are my factors? X plus 2.
This way.
Uh-huh. That one's going to show up twice at least. And then x minus 4. But now they gave us one more piece of information. They gave us a point that it has to go through, right? Which was the point 0, negative 1. So we're going to have to look at this vertical stretch in order to hit that. So we want the point 0 minus 1. So I'm going to plug in minus 1 equals a times, what, 2 times negative 2 twice, times negative 4, since I'm plugging in 0 for x everywhere. So minus 1 equals a times, what do we have there? Negative 32, I think. Did I do something weird there? That looks very different than, well, okay, let me show you just what they, oh, I see what's going on. I'm looking at two different problems at once. And I used the wrong point. Yeah, so 0, 4 is the point for this one. So let's do it with 0, 4. And so then when we plug in, we're going to have 4 plus 2. So we'll get 6. 4 minus 2 squared. So we'll get a 4.
Wait. 0, 4.
Yeah, that seems strange, doesn't it?
No.
This is 0, 4, so you gotta plug in the 0 for the x.
Oh, yeah.
So it's gonna be negative 32.
Yeah, our 4 goes where? Our 4 is for the f of x. Right, okay, there we go. And then plug in the zeros like we did before on the other one. And so we have 4 equals, and now that's going to be a times negative 32. And so we're going to get a equals, divide, you're going to get negative 1/8. Okay, so then what we have found is that this should look like, what, minus 1/8 x plus 2, x minus 2 squared, times x minus 4. Okay. Okay, so probably tomorrow we ought to use one like that to do a full review of this section. These are all kind of the same. Yeah, so let's use kind of those last couple, if you have questions on them, to review. These are just kind of bringing together everything that we did today. And we'll move on to section 3.2. So bring your questions about this one and we'll keep going. All right, cool. Have a good rest of your day. Thanks.